So up until last week, we talked about predictive AI or discriminative AI, where the goal of the model is to predict the label for the content it was fed to. In generative AI, the content is the output of the model. So the goal is not to predict the label, but rather to generate content. And content comes in different forms. You have audio, text, video, images, and because of that, you could have all these different permutations of generative AI, where the input can be text and output could be audio, and all these different kinds of mix and matches. The one that I focused on, and I'm going to continue talking about for the rest of the semester, is text to text with large language models. The input is text, the output is text. And the reason I want to focus on this is two things. One is that text as output is very useful, as evidenced by Copilot, by translation apps, summarization, and others. But more importantly, these large language models have good reasoning capabilities. You can think of them as reasoning engines, as very inexpensive brains that you can plug into agents that you will talk about later, or into robots. And that reasoning power is going to be a huge enabler. So we're going to focus on that. I just mentioned that these large language models are really good at reasoning, but they're not perfect. And the assignment was for you to try to push them to their limits and to see for yourself that they do fail. I have a few examples here. And by the way, these examples and pretty much everything else that I talk about is inspired by what I've learned from Andrej Karpathy. So here are the examples. First one, essentially the task is to multiply these two numbers. And here I have it, these two. And the output is this. If I pull up my calculator, these two numbers, multiply them, it gives me a different numbers. They don't match. So simple multiplication failed. Let's look at another example. So I'm going to put this here. Essentially, the ask here is to count the dots here. There are actually 80. And it says 74. Let me remove one of the dots. See if it gives me 73. Now it says 94. So that's the second example. Third example. How many vowels in the word Philadelphia? This is not Philadelphia. I intentionally misspelled it. But nevertheless, it should be able to count the vowels in it. The answer is 6. Let's count it. I, A, E, A. There are 5. Right? So these are some examples of where the language model can fail. And by the end of today's lecture, you will have an understanding on why it fails in such simple tasks. But let's go back to that big picture that I presented last week. LLM takes a prompt, which is a text content, as input and predicts the next word. Once it makes a prediction of the next word, it attaches that next word to the end of the prompt, and now it has a new prompt that can feed into the LLM and predict the next word for that. And it does that in a loop to provide the response. So I'm going to demonstrate this now. If I go to this website, let's give it a minute. This is a visual representation of GPT-2, which is an older language model. And as you can see here, it says it's downloading the model parameters onto my laptop, so it does it on my machine. But let me delete all this. This is the prompt here. I'm going to say, I am happy. Generate. So on the left, you see the input, I am happy, the prompt, to be fed into this huge model over here. And then the output is this. The output layer of this deep neural net has as many neurons as there are words in the vocabulary. And what it outputs is a number between 0 and 1 for each of these neurons. And that output is the probability that that word, or the word it represents, is the next word in that prediction. So here, for I am happy, it predicts that 2 has 78% probability. So it picks that. And as a matter of fact, it already appended it to I am happy. Now if I run it again, the input is going to be I am happy 2, and just creates the next, predicts the next word. So if I go to ChatGPT, say, tell me a story, and if I send it, it says funny, inspirational sci-fi. Let's see what happens if I run it again. And now it created something completely different. So if you want, pause the video, think about how is it that this deterministic mathematical expression results to different responses. Right? So here's the answer. The model doesn't simply pick the most probable answer as the answer. What it does is that it samples from these words with the probabilities that it produced, which means there is 78% chance that the word it will return is 2. But there's also 11% chance that the next word it will predict is that. And there's a 6% chance that the next word is with. And if you think about something like this, given how many tokens are there, how many predictions the model has to go through, it's almost for sure that it's not going to pick the same exact next words every time that you run the model or run this prompt. So that's why you get the variations in your model output. We talked about the output part of this, a little bit about the input part. Let's talk about the model itself very briefly, what comes between from here all the way to here. This model type is called a transformer, and you see the name of this website is Transformer Explainer. The transformer architecture was developed and published by Google in 2017, and pretty much all the hype or advancements in AI that we see today stems from that one development. What transformers are really good at is modeling sequential data. If you think about this sentence here, I am happy, this is a 1D array of data that is fed into this. There's a sequence that is presented here. And I want to give you two examples to illustrate why the sequence is so important. Why can't you just take these 3 words and irrespective of their sequence, just dump them into the model? I'll give you 2 examples. 1, consider the following sentence. John loves Mary but hates Jake. Now, this sentence has a very clear meaning to it, but if you disregard the sequence and mix and match, you will get completely different meanings and ideas. You could say Mary loves Jake but hates John, for example. So the sequence matters. The second example is in computer vision, in images, if you think about it. So you have these pixels. The pixels each have some light intensities, and then when you lay them next to each other, you arrange them well, you can see an image on the screen. Now, you can see an image on the screen only because the pixels order is correct. if you mix and match these pixels and arrange them in just random order, nothing meaningful will come out of the screen, right? So in images also, the sequence, the order at which these pixels are placed matters a lot. And before transformers, it wasn't easy. It was really difficult to model this kind of sequential data, but transformer does a great job at that. I just mentioned that LLM or transformers, they take a sequence of symbols as input. And now you have to think about, how am I going to transform my prompt into a 1D array of symbols, into a sequence, into a list. Okay? Consider this sentence. I ate some cake and gave some to a friend. If I write it in Python, that would be just like one big string. How can I convert it to a sequence? The simplest way is to chunk it by words, right? By separate them by space. So I becomes one word, 8 becomes one word, some becomes one word, and now you have an array of all this. Actually, would have an array that has a length of 10. The problem with this is the vocabulary, the corpus of all possible words would be millions and millions. Consider not just the Oxford Dictionary, but all different languages. Now add uppercase, lowercases, add misspellings, add nouns that are not in dictionary, like my name wouldn't be in a dictionary, and programming languages, right? So you will end up with a huge vocabulary of possible words. And that is a problem, because if you go back to this transformer, the output layer has the size of your vocabulary. And actually there is other layers that have the same size as the vocabulary. So your model will be too large, it's intractable, you can't work with it. Well, it turns out the text that is rendered on your screen is in fact essentially originally 0 and 1s. So you could represent it with 0 and 1. The beauty of this is that the output layer of your neural net will have only one neuron, and that would be a value between 0 and 1 for the probability that the next token, next word would be a 0 or a 1. The problem with that is now you're ending up with these huge sequences. The length of your sequence that we call the context window becomes too big. And in the transformers, this is a very precious resource. And there is a limit to how many items in the sequence a transformer can take in. That's a design choice when you build your transformer, but once you settle on that, you can't exceed that. And the computation size and actually the model size itself will get bigger with the length of the sequence. So with these two examples, now you have this intuition that you need to chunk these sentences into symbols in a way that minimizes the length of the sequence, the context window, and also minimizes the vocabulary size. It's a dance between these two. You can't accomplish both at the same time, but you want to arrive at the best balance. Here's an idea. You can take a sequence of 8 of them, which is 1 byte, and represent it with a number. Right? Each byte can be represented all the way from 0 to 255. And now you have something where the vocabulary is only 256, which is great. It's not as good as 2, and it's not as bad as millions and millions that you had up there. It's only 256, and the length of sequence is not that bad. It's much better than 0 and 1s. It's not as good as the word level chunking. It turns out in language models, you can't live with something like this because the length of the sequence is still too much. You still want to shrink it more. to take advantage of what the LLM has to offer. And this, by the way, I think is like 40 sequences. So 10 words became 40 sequences. Here's how you can make it smaller. And by the way, just a little terminology, these numbers that represent a chunk of text, we call them tokens. And this process of taking text and converting to this sequence of numbers is tokenization. All right, let's look at how we can make this even smaller in size. If you pay attention, there are a lot of repetitions of 101 followed by 32. This pair occurs quite a few times. If I continue looking, here's one, 101, 32, and there is more. Let me see if I can. Here is another one, 101, 32. And that is actually E followed by space. So what you can do here is to mint a new token. We call it 256 because right now our largest token number is 255. So I will have 256, which represents 101.32, and the result will be something like this. You can see the sequence got shorter, and there is no 101.32 pair anymore. Instead, you have 256. Now, what happened here was that you made your vocabulary a little bit larger and your sequence length a little bit smaller. And you can keep doing it and keep doing it until you feel like you have reached an optimal point beyond which your vocabulary is just getting unreasonably large and the sequence length is not getting much smaller. And in GPT-2, that was about 50,000 tokens. In Llama 3 and GPT-4, it's like 100,000. Okay? So let me show you how this fits into that initial picture that I showed you. Before, I said you have a prompt, goes into the LLM, and what comes out is the next word. But to be a little more precise, I should say the prompt goes through the tokenizer, and then the tokens are fed into the LLM. The LLM predicts the next token, and that token is decoded back into text. So if I say, I love, as prompt, the tokenizer translates this into 1842, and the LLM predicts the next token to be 345, and that is decoded into U. Okay? So let me show you in practice. Here's a web application for tokenizing prompts, so you can see what happens. And I'm picking the tokenization for GPT-2. If I say, I love, it turned into two tokens. I is token 40, love, actually space love, is token 1842. And that's where I got my numbers from. But what if it was capital LOL? Well, it becomes a different token, right? What if I have capital L, lowercase o, capital V and E? Now love has become two tokens. And the reason is, in the corpus of internet, in the text that's on internet, you don't find uppercase L, lowercase o, uppercase V, lowercase e very often. And for that reason, it didn't warrant minting a new token for this pair, for this combination. And this becomes 3 tokens. This is tokenization. And now that you know what tokenization is, we can go back to that assignment. So this was the prompt that I fed into ChatGPT. Well, ChatGPT, the first thing it does, now you know, is that it takes that and turns it into an array or a sequence of tokens. And this is what the model actually sees. Now, if I hover over 3251, you can see this is 2 tokens. Space 3 is 1 token, 251 is another token. And if I hover over this other number, space 76 is one token, the other one is another token. Now you see why it wasn't able to multiply them correctly. Now the reason is the model has no idea what these tokens really are. It doesn't know that this is a number like this and the other one is a number like that and what their multiplication mean. It just knows what is the more likely token to come given the past tokens, considering what has been common on the internet. Counting dots. What you'll find here is that all these purple like highlighted dots is one token, this is one token, and this is one token. Again, it has no idea how many dots are in these tokens. It just knows that there is a token number, whatever. Now, I want you to watch this. One dot becomes token 13. Two dots is token 492. Three dots, 986. Four dots. You see, 4 dots is one token. And if I continue doing this, there are different tokens assigned to the different number of dots. But if I continue, now you see, for I don't know how many I got here, but that became 2 tokens. If I continue, there's 1 token, 2 token. That's why ChatGPT wasn't able to count the dots, because it doesn't see the dots. It just is one token that represents whatever that text was. And just for the fun of it, let's see what Philadelphia. All right, if I put Philadelphia spelled correctly, it's 1 token because it happens a lot on the internet. But if I do this, it knows AA is 1 token, but it doesn't know how many A's are there, or how many vowels are there. That's why it can't do a good job at counting it. It turns out tokens are the currency of language models. The vendors like ChatGPT and Claude charge you by tokens. And my goal for this assignment for you is to understand that dynamic a little better, because you're going to be consumers of this AI. It's good to know the constraints and the cost of it. So here's the problem. Suppose I want to take a book that's 1,000 pages long and summarize it into 10 pages. In theory, that could be pretty simple, where you go to ChatGPT, say, summarize the following text, and then just paste or attach the entire text, right? What I want you to do is to first figure out how much it's going to cost. Is it like a couple pennies? It's a couple dollars? It's like $50? And pick a model from OpenAI. Or if you have other preferences, that's fine, but let's just say for default, I'm going to say OpenAI. There are different models. Look at their description and determine which one you want to choose. And finally, can you even fit all that text into the language model? If you remember, I talked about the context window, the number of sequences that you can feed, and the model can't take beyond a certain limit, which throws error. Think about how many tokens you're going to end up with for this task. Does it fit into the model? If not, think about how you would rectify the issue. All right. Very briefly, I want to talk about training GPTs. Well, the first step is to collect data by crawling the web and extracting all the text. And there is some pre-processing and cleaning to do, but what you're going to need is just a huge corpus of text. And a good example of that is this publicly available data set called FindWeb. It's just the result of what I just described. Crawling the web, cleaning the text, and then storing it. Here is one example of it. log in, please enter your E-code to log in. Forgotten your E-code if you're blah blah. And this is the website, the URL where the text was found. So you have all of this, and if you want to know how much of this we got, the answer is 15 trillion tokens. So you got all this text, you run it through the tokenizer, because if you remember, language model has no understanding of the language, it has understanding of tokens. This gives you 15 trillion tokens. And let me show you what you do with that. Let me see if I can copy this. So you have this text. I'm gonna go to tokenizer. So you tokenize this. Now this is everything you got. You want to train your GPT with this so that the GPT can predict the next token, given that it's learned from all this. The way it works is that you take this one, say predict the next token, and the correct answer is this. And now you take these two, predict the next token, and the correct answer is this. This is supervised learning, essentially. Your LLM is in fact a classification model where the number of classes equals the size of the vocabulary, like 50,000 for GPT-2. Anyways, you keep continuing like this until you reach the context window limit of that model. So you can't include any more in that sequence. After that, you just step forward by one token, and now, like, this is my input, predicts the output. This is my input, predicts the output, so on and so forth. That's what the training is about.